Hi, how's it going? I'm going to have a look at pointers today. Settle in, it's going to be a chill session. I'm currently cutting down on coffee, getting all these horrible headaches, but I've got a tea with me, so I guess that's the same thing. And let's get into it. So we want to work with pointers, and I'm just going to investigate some different things we can do. I think in a previous video in this series, I looked at raw pointers, and I'll sort of start off with that. But before we can do anything, I'm just going to define a simple class that I can use for these experiments. There we go. About the, just a nice simple class. It has some data members, it has some methods. There we go. So first of all, I'm just going to make a simple function which deals with this class without using any pointers. So there we go, we've instantiated a rectangle. Now we'll just sort of, I guess, check the area, check that the thing works, and also check what the memory usage is. There we go. As a matter of fact, let's just check that that's working. So we'll start the program and just jump right into that. Give it a shot. Okay, great. So we see we've made the rectangle. We can confirm that it looks like it's working like it should. And then at the end of the function, because this object goes out of scope, it is automatically deleted. Now, when we instantiate an object like this, it sits on the stack. And like I was going to do before, let's have a look at how much space that's using. There we go. My rect occupies 16 bytes on the stack. I mean, that makes sense. We have 4 floats, which are 32 bits, so 4 times 4 bytes. Yep, perfect. Now, there's a few reasons we might want pointers. One reason we might want pointers is to have basically access to the underlying object, so that if we change it at one point in a function, it will be changed everywhere throughout the whole program. And secondly, so that we can pass things around with less memory usage. So currently this is using 16 bytes. We could allocate that on the heap, and then the pointer to that would only be 64 bits or 8 bytes. And that doesn't change as we add more data members. But I'm sure you guys already understand how all of that works. I'm just recapping it. So the thing we can do, besides using no pointers, is to use a pointer. I'll call it raw pointer. Okay, so I have a pointer to a rectangle, and this pointer is created with the new keyword. And then in order to call methods on it, like, I'm sure none of this is new, but let's just do that stuff anyway. Now, if we run this, go ahead and go. Alrighty. So, no pointer, we create the thing and it's deleted. Raw pointer. So we create the thing on the heap, and then we have a pointer to it. And yeah, it works the same way, but it's using only 8 bytes because a pointer is a 64-bit address in memory. So we're using less room on the stack, which is really good, but note that it's not being deleted. So the thing in C++, and this is what I'm finally getting around to, is that with pointers, regular raw pointers, you need to, create one with new and then delete it. So then we need to go delete my rect. And if we don't do that, there's a memory leak. which is an issue. There we go. And yes, same as before, except now we can see that it is being deleted. The destructor is being called. Great. Now, this is one of the points where people start to get annoyed at C++ because it's fiddly. And I'm not saying that this per se is fiddly, but when the program gets larger, when the system gets larger, and we have, say, multi-threaded code or something, we have an object which is being created somewhere, but it's being referenced at a bunch of different places, then it can get difficult to manage memory and say, well, where should this thing be created? Where should this thing be destroyed? What should be in charge of doing the destroying? Are we making sure that everything else that refers to it knows that it's been destroyed? And things like that. And honestly, personally, my response to these sorts of issues is practice. Get good. I unironically say that. I've been through enough painful experiences with pointers that I you get a feel for it. But having said that, there are better ways. And a really cool thing is Smart Pointer. And I say Smart Pointer, there's actually a whole bunch of these different things, but the one that I'm going to focus on is called a unique pointer. Because a unique pointer is, what am I thinking? A unique pointer is a very lightweight structure. Now, the basic idea, I know I'm bouncing around a little bit here, but when I instantiated this object directly on the stack, the moment it went out of scope, the destructor was called on it. And in a similar way, we can create a pointer object which is allocated on the stack, and it manages a raw pointer. And then when that object goes out of scope, it gets automatically deleted because it's just a temporary variable. It's just an RAII object. When it goes out of scope, it gets deallocated, and its destructor will free the underlying pointer, which is mapped to it. So enough talk. Let me demonstrate a simple example. Okay, so we have this unique pointer, and then that's a generic, and we need to specify what sort of thing it's pointing to. And now what I'm going to do is I'm going to instantiate this just the same way that I instantiated the class before. For real, I just looked at my screen like an idiot, like a fool. I just needed to... jeez. I got to stop doubting myself. Okay. Anyway, so there we go. Just like I said, we've instantiated this just the same way as before. It's basically wrapped up this raw pointer. It's managing that thing. So, well, we can't really delete my rect because it's not one of those things. But have a look at this. So I'll just go call that one. Run that and have a look. So it does its thing, makes a rectangle. Yep, it uses the same amount of memory because with a unique pointer, it only has one data field, which is the raw pointer that it's working with. So it's a very small struct, very small object. And the moment it goes out of space, goes out of scope, we don't have to explicitly delete it or anything. It automatically gets deleted. So then the next question is, okay, this is fine. We've got a unique pointer. What can we do with those things? How can we work with these? So I'll just define a few, what am I thinking? I'll just define a few functions here. Okay, so one thing we can do is we can create a unique pointer and pass it out. Return that. Do all this again, unique pointers 2. And I will put these printout signals here. just to be super explicit about where things are being created and destroyed. Because what I want to check, what I want to check is that, yeah, the moment this thing goes out of scope, it'll be destroyed. But if we return it from a method, does that count as going out of scope? Let's investigate. I mean, if it does, that's a pretty poor implementation. Let's check it doesn't do that. Alrighty. So now we'll just get this from the function up above. There we go. Okay, so have a look at this. We start the method, start the function. I always get those two mixed up. A method is a function within a class. A function is just a function. Okay, so start the function. It starts off the other function to make a rectangle. And although that unique pointer is sort of out of scope, but it gets returned. So, you know, C++ is pretty clever about that. So it doesn't get destroyed. We can get it back. We can work with it. Okay, everything works the same as before. All right, so now we can modify things. So let's go void modify rectangle. So we want to do something like this. We want to grab this pointer and just modify its fields. There, all it does is just increase the width and height. Okay, so have a look at this. So what we want to do is we want to pass this in and modify it. Makes sense, but C++, the linter picks up on this and says, wait a second. When we pass, what am I thinking? When we pass unique pointers or anything into an argument, that's actually a copy by value. Now we could get around this by taking in a reference to a unique pointer, but if we're taking in a reference, why not simply take the underlying reference to the object? And then what we can do is we can still dereference a unique pointer just the same way that we would any other object. And there we have it. So we can, what am I thinking? We can access things. We can access the underlying pointer just with the regular arrow operator. We can dereference with the star operator just the same way that we would a raw pointer. Yeah, it's just very nice. So we can run that, give it a shot. There we go. Yeah, everything works. We modify it, the area changes, but everything's still the same. Okay, so that's all well and good, but we might be thinking, all right, once we make a unique pointer, the underlying object, the underlying raw pointer, is it locked into that? And I mean, I don't know, is it? Well, it turns out it isn't. So what we can do is we can go get the raw pointer, which this is pointing at, with the get method. Yeah, we can get it. We can delete it, just like that. Another thing we can do is we can call release, and release will essentially just set this unique pointer so that it's no longer constrained to be looking at this thing. So if I were to do this, then my rect could still be pointing to a pointer, the memory for which has been deleted, but release will pretty much do what it says. We can then set this to another one. So we'll just go construct a new object, just like that. Great. And now another way we can manually delete this is, with the reset method. So release sort of releases the pointer's hold on its managed resource, so you can do whatever you want with it, should you ever want to, do that. And reset will manually delete the reference, the object and everything. But also, of course, the moment this goes out of scope, it will automatically be deleted anyway. So as you can see, give this a shot, and yeah, we created 2 rectangles, and those 2 rectangles have been destroyed. Okay, so. Like I said, there are other types of smart pointers, but I think really unique pointers are the best. If you're going to use anything, I would use that. But just for reference, we've also got a shared pointer. Now, a shared pointer is an object that manages a raw pointer, but it also has a reference count. So there's many, it can be referred to by many other objects at the same time, and it is not deleted until all of the objects that refer to it go out of scope. So there are some benefits to this, but also there's some overhead. For one thing, the size is double, 16 bytes, because we have 8 bytes for the actual pointer that we're managing, and then another 8 bytes for the basically the metadata, the struct, which is keeping track of the reference count and stuff. So that's not great. And then we also have a weak pointer. Now, a weak pointer basically can access the raw pointer, which is being accessed by many shared pointers, but it doesn't increase the reference count. And that can be used in some cases, but, at the end of the day, unique pointer really is the best. Anyway, hope you enjoyed this little rundown. Maybe it's given you some things to think about. I certainly had fun looking into the topic. And yeah, have a great one. I'll see you again soon. Bye.